Now you're asked to consider whether these approximations are high or low. Well, if you draw a normal curve, it starts out level and it's got kind of this downward concavity, then it has kind of an upward concavity. Terminology you might not be completely aware of at this point, but the function kind of humps up over the trapezoids here and here, and actually the graph should go through this point. Drew it a little bit high, but on both of these trapezoids, because of the curvature, the way the graph is curving, opening downward this way, concave down, the graph is going to lie above the curve. So these percents and so forth are actually underestimates on the first couple of trapezoids. After that, the graph changes concavity. It kind of curves up here. Now, the exact point at which it changes concavity isn't necessarily right here, but in any case, it changes its concavity, so the graph goes down below the trapezoidal approximation, and the actual area is less than the areas indicated here. However, we can see that the graph stays pretty darn close to the curve, and these approximations are not very far off. Okay, more on the first few trapezoids than on the last few. They're a little further off in the first few than they are in the last few, and you can think about why that would be. Now you're asked to pick one of these intervals and refine the calculation. Okay, so I'm going to go ahead and pick, let's say, the third interval, and we're going to refine the calculation of this time we're just going to refine the calculation of the area on the third interval. Your table gives you values of the function. It gives you the graph altitudes that you would use between z equals 1 and z equals 1.5, corresponding to the third interval. And we have a table right here. So you should think through how you would use that table to do a refinement on the third interval. Okay, the refined values as they're given are 0.420 at 1, and then at 1.1, 1.2, 1.3, 1.4, 1.5. You can read it yourself from the table. You got 0.378, 0.337, etc., down to 0.225. You can verify that the slopes that result from these numbers are as indicated: negative 0.44, negative 0.41, negative 0.40, etc. And that progression doesn't look, you go down by 0.03 here, then 0.01 here, then 0.03, then 0.02. That's not what a smooth curve would in fact do, but because of round-off errors, round-off uncertainties, it can look like that. But we see a steadily decreasing slope, which is consistent, steadily decreasing magnitude of the slope. The slopes are actually increasing. If you go from a negative 0.44 to negative 0.35, you're gone from further below zero to not as far below zero. So these numbers are actually increasing, but their magnitudes are decreasing. So the steepness is decreasing, so the graph is curving somewhat this way, consistent with the way we drew it over here. You weren't actually asked to do this, but that does confirm some of the things we're talking about over here about the concavity of the graph. Now, the calculation of the areas is very straightforward. Here are the areas, and the total area here is 0.159. Now, previously we got 0.16. That could have been 0.159 rounded up 1 unit. However, if we take this altitude and this altitude from 1 down to over to 1.5, instead of the 0.42 and the 0.22, we actually use these more accurate values. We get a total area of 0.161, meaning that there's, by refining our estimate, by looking at more and more points, we got a more accurate picture of our total area. And we noticed that this total area is lower than this one, as we predicted it would be based on the concavity of the graph. So I write the statement that the refinement, as we go from here to a more refined model, yields less area as we expected because of the concavity of the graph, and that we have roughly a negative 1% adjustment. Okay, that's 2 parts in 160, and 2 parts in 200 would be 1%, so a little more than a 1% adjustment downward in the estimate of our area, meaning this is going to be pretty close to the actual area. Last comment, these percents were percents of the area under half of the total normal curve. To get the percents of the area under the entire curve, we would take half of these numbers, which would give us these numbers, and the accumulated areas would be these. And this is consistent with what you would get if you used a Z table. The main anomaly would be this 9 would be a 10, and these would adjust slightly. I'm going to give you a little more information. Your function here is y equals a e to the negative z squared over 2. And you can use any value of a. Okay, so you can evaluate this function. You pick any number for a. Pick a equals 1 if you like. Well, when z equals 0, e to the 0 is 1, so you're going to get 1 for your middle altitude. That's going to give you bigger areas, but when you calculate these percents, they're going to come out the same. Now, you might calculate them to more significant figures and get more accurate versions, but you're going to get more accurate or less accurate, depending on how you round off, versions of the same percents. There might be little differences. This 9 will probably become a 10, or this 4 will become a 5. Now, just to be a little more clear about this A thing, if you make A bigger, then all these graph altitudes are going to get bigger, which means all your areas are going to get bigger and your accumulated areas are going to get bigger, all in the same proportion. So that when you divide the accumulated areas by the total accumulated area, you're still going to get the same percents. Of course, percents might be more accurate versions of these numbers, as we've said, if you use more significant figures in your calculations. Now, there's a specific value of A, because obviously if we make these numbers a little bigger, we could get a total accumulated area of 1. If we make them a little smaller, we could get a total accumulated area of 1/2. Now, that's on half the graph. Why would we want to do that? Well, it'd be nice if the total area under the whole graph was 1, then we wouldn't have to do any divisions over here. We'd have an area of 1/2 here, and that would be correspond to the accumulated area from here to here, which is half the area of the whole graph. We should get 0.5 if these if we want the accumulated area to correspond to 50% of the entire graph. So, and I'm going to give this away because there's no way you're going to figure this out. You have to get pretty advanced in undergraduate mathematics before you can figure this out at all. But the value A equals 1 over the square root of 2 pi. If that is the value of A, that gives you total area under the curve of 1, and that's extremely convenient. And that would be a good exercise for you to do. Create this graph using A equals 1 over the square root of 2 pi in evaluating the graph altitudes, i.e. the values of this function.